Okay, so here I just want to remind you of what we did in chapter 5. In chapter 5 and chapter 6, we used op-amp. So in chapter 5, I explained what is op-amp and how can we use it in different circuits. Okay. Also, I explained if you have a circuit, how can you analyze the circuit? Okay. Simply what we did. In case of op-amp, we only use two things. We only use two things here. V1 is equal to V2 in our analysis. Also, I1 equal to I2 equal to 0. But the current at the output here is not 0. You cannot assume that. You understand what I'm saying? So that's what I did in chapter 5. Okay. If you forget or you have all lectures are recorded, so you can go back to the lecture and you can see how I analyze the circuit of op-amp. Okay, I only did two things all the time. For sure, in addition to Kirchhoff current law, Kirchhoff voltage law, Ohm's law, in addition to all this stuff, what is efficient here in this op-amp is always this volt here is equal to this volt. Okay, that's number one. Number two, the current here is equal to 0. Based on these two things, I analyzed all the circuits. That's what I did in chapter 5. Okay. So in chapter 5, I did number one, I explained how can use op-amp to create inverting amplifier. And this is the circuit of inverting amplifier. You can notice always we have feedback from the output to the negative input here. Always we do that. Okay. So you can see here we have R1, Rf here, we have V output, V input is here, okay? And the relation between output and input is actually V output equal negative Rf divided by R1 times V1, V input. You can, what I did here, what I did in lecture, I did analysis. So I explained how I got this formula from this circuit. You can do it. So this is for inverting amplifier. For non-inverting amplifier, it's almost the same like inverting amplifier, but what I did, look at the difference between them. What I did, V input here, ground is here, so I just switch it between these two. Here it's ground, here it's V input. By doing that, now the relation is V output equal to 1 plus Rf divided by R1 times V input. Is the relation between output and input. And then also I explained voltage follower, and this one is closer also to this one. All what I did, I just cancelled this R1 here, and I made this one short circuit. Okay, V input here, V output here. This one V output equal to V input. Okay, and I already explained in the slides why I need something like that. V output equal to V input. It looks like a short circuit. Okay, no, I explained why it is important. Okay, in the slides, because simply you have here input current is almost 0, but you can have a big output current. Okay, so you can go to the slide. I already explained this one. Yes.
So it's going to be
Yes.
circuit drawings. We don't have to calculate.
No, you need to memorize this circuit. In the coming on Thursdays, it will be a quiz. In the quiz, I will ask you to draw the circuit and give me the formula. Okay. Not for everyone. Maybe I'm gonna select 3 or 4 of them, but you need to learn all of them for sure. Okay. So we have other things I'm gonna explain now, but this is the circuit. This will be in the coming quiz on Thursday. Okay. It should be very easy quiz. You should not use the points of this quiz. It's very straightforward. I will ask you, draw the circuit of non-inverting or inverting or voltage follower or whatever. Give me the relation between output and input. That's it. Okay? No calculation, nothing. Okay? So after that, also in chapter 5, I explained adding circuit. So adding circuit here, as you see, this one, I just want to show how it is easy to memorize. It's not hard. Why? Because they are very close to each other. For example, adding circuit here is just similar to inverting amplifier here. Just similar. It's almost the same. But instead of having here, this part here, R1, V1, I just repeated it. That's what I did. So here, one here, and then I did another one, and so on. Okay. So this is addition. This circuit can do addition. Okay. So that's why you see here V out is here is equal to negative Rf divided by R1 times V1 plus RF divided by R2 V2, which is the same formula like this one, by the way, okay? But here, because we have only R1, here we have R1, R2, R3, and so on, okay? So, and then in a special case, if I can make R1 equal to R2 equal to Rn, so all these resistors here are equal. In this special case, this is the formula, final formula here. V out equal to negative Rf divided by R times V1 plus V2 plus Vn and so on. Okay. So this circuit, it can add signals together. Is that okay? Any questions? Also, we have here, we call it differential circuit or subtractor. So here we have differential circuit or subtractor. So this circuit can do subtraction. Okay. By the way, there is a trick I can tell you about the trick here. This one, although this circuit here is doing addition, I can simply also do subtraction here. You know how? All what I do is instead of inputting V1, I'm going to input negative V1. That's it. So here in this case, this one here is going to become negative here. Okay. So by this way, you can do also subtraction here as well. Okay. How can you, is it easy? Instead of inputting V1, you can input negative V1? Yeah, it's very easy. What you have to do is, and that's what I think it's already explained in the slides, what you have to do here is, if this is V1, okay, this is positive, negative grounding. So actually here, this is positive V1, okay? If I want to input negative V1, all what I have to do, just I'm gonna change the polarity, switch the polarity. So ground is here, this one is still V1, this one here, this one, okay? So because this is grounding, this one should be negative V1. You get what I'm saying? So it's very easy. If you have a source, you can input V1 or negative V1. Just you can change the polarity, okay? But anyway, so here in this subtractor circuit, we have here V1, we have here R1, okay. We have here I'm gonna call it R2, and then here in the positive side here, I'm gonna input here, we have R3, we have R4, and then here I'm gonna input V2. So here the output is, the output, I will take a special case just to make it easy. You can do that in the test. I'm going to take a special case when R1 equal to R3. So when these two are equal, yeah, these two here are equal, and these two here are equal. Okay, I can take this special case. So here, if I take this special case, R1 equal to R3 and R2 equal to R4, now the output equal to R2 divided by R1, okay, times V2 minus V1. That's why I call it subtractor, because you can subtract two signals. Any questions? Yes.
Is there ever a situation, you said the feedback always goes into the negative side of the op amp? Is there ever a situation where that's not true, or is that across the board?
That's a very good question. So always the feedback has to go to the negative. Okay. Why? Because if the feedback goes to the positive side, if you have a small noise, so this noise is going to be every time it's amplified, and then the op-amp is going to be saturated. Okay, so usually we have to put feedback to the negative to keep it stable. Okay, so avoid making keeping amplifying it by the op-amp. So yes, all feedbacks are to the negative. Okay?
Thank you.
And then after that, in chapter 6, I explain two more circuits. You need to know these circuits. One circuit to do integration, and the other circuit to do differentiation. How can you do integration and differentiate? It looks hard. No, it's not hard. I'm going to tell you what is the main point here. The main point, because when I explained the capacitor, we found that the relation between IC and VC. What is the relation between current and voltage here? Okay, VC. We find the relation is IC equals C dVC by dt. So already differentiation is here. It's coming from the capacitor. Okay. Same thing. If you look at inductor, in inductor, if you have here current IL, and you have here the voltage drop here is VL, we found that the current here IL equal to 1 over L integration of VL dt. So I have one element here that can do differentiation. I have another element here that can do integration. Okay, that's why I'm gonna leverage these two to create a circuit that can differentiate the input and also integrate the input. And based on that, what I explained in chapter 6. So here is the first circuit here for integration. We have here R. If I put the capacitor here again, V output here, this is ground, this is V input. So here in this circuit, we found that the output equal to -1 over RC. This is R and this is the value of the capacitance C times the integration of VI dt. So here the output is function in the integration of the input. Okay. Again, in the slides, and also I explain how I was able to come up with this equation by analyzing the circuit. So I analyze the circuit to get this equation. Okay. Same thing here if you want to do differentiation. In case of differentiation, it's going to be exactly same circuit. All what I will do, I'm going to switch. I'm going to put here the capacitor here and the resistor. I'm going to put it here. Okay. That's why this is the circuit here. And we found that the output equal to -R, this is R, C, dVi by dt. So the output is actually function in the differentiation of the input. Okay, guys, any questions? So now, based on what I did right now, guys, here you can see using OM, I can do some mathematical operation like the amplifier. By the way, amplifier, this is like you multiply by constant value. You got what I'm saying? So if you wanna multiply by constant value, so I can use here one of these amplifiers. I can add signals together. I can subtract signals. I can get integration. I can get differentiation. Okay. So what I will do right now, I can give you an equation. This equation it can have integration. It can have any of this operation. Then I will ask you to make the circuit. Okay, this is the example. This is the last example in chapter 7, chapter 6. Yeah, so this is the last example we have here. So here in this example, look here, guys. In this example, I wanna make a circuit. This circuit has two inputs, X1 and X2, and the output is Y. Okay, so the first input X1 should be multiplied by number 5. Okay, so and then X2 after integration has to multiply by 10, and then they have to be added together. Okay, so now using the circuit I explained right now, how can we make what kind of circuits I have to use? It may be one circuit, it may be more than one. Okay, it depends on the problem you have here. Okay, so how can you use the circuits I explained right now so that you can have this equation? Okay, for sure, this is amplification. You can see this part is amplification, and this one is integration. So now I need two circuits. Okay, but here also we need addition here, But when you do addition, it's already multiplied by a number. Okay, so if I go back here to what I explained, so this is the way you have to think about it. Number one, you have integrator, so you have to use integration circuit. That's number one. Okay, and then I have to add this one to this one here. Okay, I can use another. So now I can use another to do this. To do this addition, to add these two together. Okay, but how I can come with number 5 here? Number 5, it's already, if you look how the other, in the other, you multiply by a number. Okay, so you can get it from here. If the other does not do that, so maybe I'm gonna use another circuit to multiply by 5. You got what I'm saying? So the way we can do it here is this is an other circuit. No, it's normal other circuit here. Okay, an other circuit here. You need to twist this equation a little bit because this other circuit has to multiply by negative. So here, so this is x2. Here x2 is here. I will do the integration. I will do this part first. This is what should be done here in the first circuit here. So this the first circuit we will do integration here. Okay, and then after doing the integration, I'm gonna add this value to I'm gonna add it to the input here x1 here. Okay. However, there is a trick here. You need to pay attention to it. Okay. The first here you can see if you go back to the integration, there is a negative in the output here. Also, this one there is a negative. This one multiplied by negative. Okay. So to count for this negative, I didn't do anything. I'm gonna do some algebra manipulation to make it fit the circuits I have. Okay. So because this is the other has one input, and then it has to be multiplied by a negative outside here. Okay. And then here, because this one is positive, so here this one has to be negative. So instead of inputting x1, I have to input negative x1. Okay, you understand what I'm doing? What I'm doing right now, guys, is the other circuit I have, it has this format. It has to multiply by negative here. But this equation doesn't have a negative. Okay, I can manipulate this equation. I can edit it a little bit. So I can put negative here. After I put negative here, so this one becomes 5 times negative x1. Okay, that's why when I put here negative x1. Okay, what about this 5? How can you come with 5? That's easy because 5 is going to be Rf divided by F3. So if you go back, if you see how other works, you can see when you do the addition, number one, you multiply negative here. This is number one. Number two, the input you have here, you have to multiply by Rf divided by R3. So in order to get this part here, I have to make sure 5 is equal to Rf divided by R3. You know what I'm saying? So again, all what I did, guys, number one, we need to understand the circuits we have to do mathematical operations. That's number one. Number two, you need to see if you have an equation like this one, how I can implement this equation using the circuits I have. And sometimes you need to twist it a little bit, okay? Or you need to do some algebra manipulation, okay? To make it fit the circuit we have. Okay. So this part now is okay. Now let's look at the second part here. And the second part here, remember, in the second part, I don't have a problem. One, because this circuit is going to give me negative. Automatic, this circuit integration is going to give me negative. And this one is going to multiply by a negative. So I should be okay. You got what I'm saying? So that's why I'm going to input here x2. So here when I input x2, if you look at the formula of the integrator, you will see here, this one negative, this part here, negative integration. Okay? So here I don't have any problem regarding the sign because this one is what here I'm going to input x2, not negative x2, not negative x2. Okay? This one automatically, this circuit give me negative and the other is going to give me another negative. So this will cancel. Okay? But now, what is the output of the first circuit here? It's 1 over the output of the first circuit here. 1 over R1, 1 over R1 times C. Okay, this is the output here. Okay, and then this input this input here, this circuit here is gonna multiply this input by RF divided by R2, as you see here. So it's gonna be RF divided by R2 times this part here. So this is the final thing I have. Okay, so RF is gonna be RF divided by R2 is coming from this circuit here. It should be multiplied by this part here. Okay, so I have to make sure all this part is equal to 10. You got what I'm saying? So now I have to make sure RF divided by R3 equal to 5 in order to get 5 here. Number two, you have to make sure RF divided by R1 times R2 times CF is equal to 10. Okay. You can, after that, once I have these two equations, for sure, I can. This is not an equation to solve, okay? This is a ratio to whatever it had unlimited solutions. So you can select any value for R. And look again, you said the number here is going to give you 5, the number here is going to give you 10, you are okay. So there is no one unique solution. Okay. So here, for example, I'm going to select RF 10 mega ohm, then I plug RF link by 10, and then I can find R3. 2 mega ohm. So I've selected 10 mega ohm and 2 mega ohm. If you see the ratio, it becomes 5. Same thing here, RF here, RF, it's the same RF. You have to be careful here. I can't change RF. It's the same. RF is common between them. If you already selected RF here with 10, so you have to use 10 here as well. You understand what I'm saying? If I use here RF 10 mega ohm for RF, so also you have to use here 10 mega ohm for F as RF as well. Okay. After that, you can select any values for R1, R2, CF so that you can get 10. Any questions? Very important because as I told you in my email, in test 1, in the coming quiz, I will only, sorry, in test 2, in the coming quiz, I'm going to teach you in the circuits. I want to make sure you know the individual circuits, okay? The circuits that can do mathematical operation. In test 2, I will give you a formula like this one, and then I will ask you to give me the circuit, okay? So it's going to be similar to what I did here. But it can be instead of an integration, it can be differentiation, it can be subtraction, whatever. So if you have any question here, you can raise your hand. Yes.
What is what the reason for the algebra manipulation was?
Yeah.
Like the negatives or
The reason is because if you see here, I have 2 inputs. Is that okay? 1 input and 1 input, and then I want to add them together. The other I have, it doesn't do that. The other I have is going to be negative. If I go back to the other circuit, yeah, look how the other is working here. There is a negative here. RF divided by R, V1, RF divided by R2, V2. You got what I'm saying? So there must be negative here. Okay? That's what I did. Because this is what I'm going to use, right? So I have to make sure it's going to fit. So all what I did here, I took minus, I took negative here out of them, okay, this way. And then I found here, if this is an input, this is an input here. As you see here, this is an input coming from here. Now you need to decide this input positive or negative. Yes, I can make it positive or negative. As I told you, just I can change the polarity. That's it. That's very easy thing to do. Okay. So in this case, this one has to be negative. Maybe in exams, I'm gonna change this one, make it negative. So if I make this one negative, so this one has to be positive, and you have to input it x1. Is that okay, guys? Is that difficult? Same thing here for integration. I'm gonna input x2, not negative x2. Why? Because the circuit of integration itself is gonna multiply by negative already. You know what I'm saying? So this circuit is gonna multiply already by negative. Okay? So here, so this part here is gonna it comes, this part here, it can come from here, and then after that you need, and this is the most important part, you need to find the parameters, the different elements of the circuit, see what values you need to select for these elements in order to get 5 here and in order to make this one 10. Any questions? Okay. So in this one, there will be a question like this one. I will give you a formula. Okay. It can have this formula. You can use any circuits. As the circuits we have, well, it should be easy, hopefully. Okay. So now before I move to before I start the next chapter, I want to talk quickly about my observation when I created the test. Yeah, but before that, as I told you in my email, for test 1, this will be a question in the test. It will be something equation, something like that. For sure, it's not going to be identical to this one. I will do some changes for sure, but it will be the same thing like this one. Then I will ask you to draw the circuit, design the circuit. This is one question. The second question will be from from chapter 6. From chapter 6, you have so many examples here. Look here, I explain how can you analyze these circuits. So I will give you a circuit, and then I will ask you to analyze it. Analyze it means found the relation between V out, V input, find the current, whatever, similar to what I did here in this chapter. So I can give you one of these circuits, okay? And then I will ask you to analyze these circuits. That's it. So you can see here, nothing is new. All what I did here, I used the Kirchhoff current law, Kirchhoff voltage law, Ohm's law. On top of that, I used here these two factors. The input current here is 0. Is it voltage equal to this voltage? Okay, so you need to study these examples here. Okay, so in all this chapter, that's what I did in the whole chapter. I analyzed this circuit. Okay, the circuits that have op amps, I analyze them. Okay, so you need to know how to do it. Okay. The third question will come from next chapter, so I will tell you when I come to this point. And so the test is gonna have 3 questions. But before I move forward, as I told you, I graded the test by myself, and I have 2 main observations I found, so I need to address them here. One of the observation, and not many students, but I feel like this is something I need to address. Not many students have this mistake. So you remember this question? In this question, I asked you to write the equations. Okay. The mistake I found was, look here, guys. You can assume the direction of the current as you want. It doesn't matter. Okay. So, for example, I can assume the current here would be this way, the current here would be this way, the current this way, and then I can assume the current this way. Okay. I can assume you can assume any other type. Some students assume other direction. I'm totally fine with that. That's not the problem. The problem is if you assume the direction this way, in the 3 equations, you have to use the same directions. What I found, one equation, you assume the current this way. Second equation, you assume the current this way. Okay? It's not going to be true. You understand what I'm saying? So in the beginning, you can assume whatever. So some students assume, make it this way. I'm totally fine. As long as you are using the same direction. As long as you are using the same direction in the 3 equation, it's okay. Okay, but I found some students in one equation, for example, they assume the current this way, and then give me one equation. Okay, when you calculate the equation of V1, for example, I found that one student or some students assume the direction this way, but when you come to V3, for some reason you made it this way. Okay, and then you did the calculation for the next equation this way. Is this not going to give you correct results? You have to stick. You have to put some direction, and then you can use it in the 3. It doesn't matter what direction, okay? But you have to use the same direction in all equations. This is one thing. The second thing, some students here, this is 6 volt, okay? Some students, this is not the current, this is the voltage. So in this equation, some students put it like 6, but as when you use Kirchhoff current law here. Okay, so for example, here you have I1, you have here I2, for example, and this 6 volt. Okay, for sure, this is a volt, this is not current. You understand what I'm saying? So what is the current here? I don't know. Is there a formula to get the current here? No, it's not directly. You get what I'm saying? So here, if you have current here, I6V, if you have a battery and I give you the voltage, can you get the current? The answer is no. If you have a battery, because this current depends on the rest of the circuit. Okay, so that's why what you have to do here, you have to apply Kirchhoff current law. So there is a current here. I don't know what is this current. Okay. Anyway, but you should not use 6 volt. But again, the main issue I found here, you can assume the direction, whatever direction you want, it's okay, but you you have to use the same direction for the whole equations. Okay? Any questions? The part I need to explain in more details is actually the last question. And many students were not able to solve the last question. It's a difficult question. Although after I solve it here, you will find it was not hard, okay? But you will see them. You need to know Stephen and Norton because we are going to use it in the future. Okay, so I'm gonna solve it here. So here we have 6 ohms. We have here dependent source 2 VAB, and then here we have 6 volt. Here we have 4 ohms, and then here we have RL. And this is point A, point B. Okay, so this is an independent source. This independent source is actually 2 times the voltage here across here. Okay, I want to calculate Thevenin for this part. Okay, so number 1, I need to find VThevenin. How can you find VThevenin? You have to open the circuit. You have to open it. Okay, so here this one is 6 ohm. This one negative. This one is plus. And then we have here 4 ohm, and this is actually VThevenin is here. So if I can find the voltage drop across 4 ohms, this is VThevenin, okay? And then we have here 6 ohm, okay? Number 1, many students did this one this way, okay? However, this not there. I don't know why. So many students, once you have this one, they are not able to calculate VThevenin, okay? Some students did like mesh. You don't need to apply mesh here because you don't have several loops. You have only one loop. Okay, so the way you can solve it just using Kirchhoff voltage law. That's it. Kirchhoff voltage law, because you have only one loop here. You can apply Kirchhoff voltage law here. So if you can apply it, so it should be -6, okay, plus I 6 ohm. So here's the current I, here I, okay, and then -2 VAB, okay, plus 4I equal to 0. Is that okay? I just applied Kirchhoff voltage law here. Okay? Okay, but now the problem, you cannot solve it because you have 2 unknowns, VAB and I. Can anyone tell me what should I do? I have 2 unknowns here. And I can't make mesh, or I can't make voltage nodal or anything because I have only one loop here. Okay. Anyone can tell me how I can proceed, how I can solve this one? I have 2 unknowns, I and VA. By the way, in order to get VThevenin, it's enough to know I. Because once I know I, if I can get I, so actually VThevenin should equal 4 times I, because the voltage drop here is VThevenin. You got what I'm saying? So how I can solve this equation to get I? In the examples you have, and also the way I explained it, you need to find the relation between VAB and the unknown here. Yes.
VAB is VTH, so it's
Yeah, this is point A and this is point B. Okay, so this is, once I open here, this is VAB between A and B. You got what I'm saying? So VAB is actually the volt, which is actually VThevenin. It's actually the voltage drop across the 4 ohm. So this one is actually 4 times R. Okay, so VAB equal I times 4 because VAB is the voltage drop here. Okay, now I have one equation which is -6 plus 6I minus 8I plus 4I equal to 0. Okay, so this one 2I should equal to 6 or I should equal to 3 ampere. Once I get I, so now VThevenin now is equal 3 times 4, 12 volt. I'm done with VThevenin. Okay, guys, you see what I did? Any questions? you don't need to overcomplicate it. You don't need to use mesh, or because it's only one loop, that's easy, right? The only problem you have here is you have two unknowns, VAB and R. Okay? But still you can get relation between V and R. And that's what I did. And then I found I, then I found V. For some reason, I found some student who just made this one short circuit. I don't know why, but they made it short circuit. Okay? They just ignored. It seems like it was hard to find this relation and just ignore VAB. For sure, you cannot ignore it as a source. Okay? Any questions? Okay. Now let's come to R-Thevenin. How can you calculate R-Thevenin? I'm going to tell you, I found several students did it this way. Okay, you told us in the class, if I look this way, okay, this one, I can look this way and I can find R-Thevenin this way, okay? And this one becomes, I can make this one short circuit, I can make this one short circuit, and now R-Thevenin is actually 4 in parallel to 6. Is that true or false? Yes, we did that in the slides, yes. But what I did right now is true or false? What I did right now is false, because when I explained in the slides, I told you, you cannot use this approach if you have a dependent source. If the circuit had at least one dependent source, you cannot use this approach. You can only use this approach if all the sources you have are independent. But here we have one independent source. So if you have at least one independent source, you should not use this one. You got what I'm saying? So what should you do? What you have to do, you have to use the other approach. So you have to say R-Thevenin equal V-Thevenin divided by R Norton. So you need to find R Norton. Is that okay? How can you find R Norton? R Norton, the way you have to find R Norton is, and there is a tricky mistake here, I'm going to also talk about it. You know when you calculate I Norton, as I told you before, you have to make a short circuit this way. Is that okay? Yes, you have to make short circuit. And because this short circuit in parallel to 4, it's like you cancel to 4. No current will go to 4. All the current here is going to go through here. Okay? Any short circuit over a resistance, you cancel the resistance. Okay? But now, this is a very serious mistake, a very tricky mistake. Okay, now. Okay, so what is the value of VAB? Again, VAB is making a problem to some student here. What is the value of VAB in this case? What some students did, and this is really very tricky mistakes, some students took the VAB from here. VAB here, VAB was 6 volts, right? So VAB was 6. So some students take the VAB from here and applied it here. Do you think is that true? No, because this is a completely different circuit. So once this is a circuit, when you make it open circuit, this is a circuit. When you make it short, this is a different circuit. You cannot just take from here to put it here. You understand what I'm saying? So I found many students did that. Just took the VAB from here and put it here. No, this is a completely different. There's nothing related to this. It's a completely different thing. Okay. So what is VAB here? VAB, guys, VAB. 0. It's a short circuit. So all what you have to do here, this is 0. That's it. So here is a voltage drop here, 0. So I have 0 voltage drop. 0 voltage drop. And then after that you can use it, you can use Kirchhoff, Kirchhoff voltage law here. You can find 6 volt equal to negative 6 plus I 6 ohm plus 0 or equal to 0. Okay. And here you can find I equal 1 ohm. That's it. I can explain it a different way, because once you make this one 0, the voltage drop here is 0. Okay, I can explain it in another way. If you have a voltage source and the amount of voltage is 0, so it becomes a short circuit. If you have a voltage source and the voltage drop is 0, short circuit, anything that voltage drop is 0, short circuit. You got what I'm saying? So the voltage drop here is 0, becomes short. If you have a current source and the current is equal to 0, so now this one becomes like open circuit. But anyway, this is not the case. Okay. So once you found V-Thevenin and I Norton here, this is I Norton. You can so here we found this one 12 ohms. because rule from this one should be 12 volt divided by 1 ampere, which is I naught. And this is V7, okay? V7 in here was 12 volt, okay? This is, and then we have RL here. Okay? The next question I asked you, what value for RL that can maximize the power transfer? Okay? You know, for this circuit, if you have a circuit exactly like this one, as I explained in the slide, in order to maximize RL has to equal to 12. So it has to equal to this voltage. To maximize it for only for this circuit, we did analysis or we explained, or even we did analysis for this exact circuit. When you have a resistance here and resistance here, and you have a source here, we found for maximum power transfer, this RL has to equal to 12. Okay, this is. And now, so here for maximum power transfer, this one should be 12. Okay. And now after that, I asked you to give me the amount of power. Number one, there is a formula. Okay, you can just use this formula. As I explained it also in the lecture. The formula was for maximum power transfer. The maximum power here should equal Vs squared or V input squared divided by 4R before Rs. This one Rs. So here, which is 12 squared divided by 4 times 12. If you don't want to memorize the formula or you wanna, the other way, you can just calculate it from, here. You can calculate the current I, okay? You can calculate the current I. So here I should equal 12 divided by 12 plus 12 to equal half. So again, you can just use the formula, or you can calculate it from how much power you have here. To get the power, you need to get the current. So here the current is actually 12 divided by 12 plus 12. Oh, and you can need the voltage. To get the voltage, you need to use, you can use voltage division. Okay, so this voltage time, you can see they are equal, but anyway, let's use voltage division. So this one should be 12 times 12, which is this resistor, divided by the summation of the two resistors. In other words, if the two resistors are equal, the voltage will be divided equal. You don't even to think about it. Let me say it again, guys, because I found a lot of students still, even in the first problem. Let me tell you this. This is the way you have to do it. So you have R1, you have R2, and then here you have Vs. If I want to get the voltage drop here, it has to be Vs, okay, times R2 divided by R1 plus R2. Is that okay? But that's a special case. Yes, you can use this one all the time. That's okay, but there's a special case. If R1 equal to R2, okay, if you look at this one, it would half. So the voltage here would be divided by half. So you don't even think about it. Once I find here, for example, here I have 12 volt, and then I have, for example, 6 ohm and 6 ohm, for example. So yeah, this is 12. So this one is going to take 6 volt. This one is going to take 6 volt because the resistors are equal. Okay. Same thing for the current. Okay. You remember, or same thing for for the current. If you have here R1 and R2, if the two resistors are equal, and for example here I have 1 ampere, and the two, for sure you have a formula for current division. You can use the formula, that's for sure. But if you can find the two resistors are equal, okay. And by the way, sometimes I intentionally make it equal so that I can make the calculation easy. You don't need to calculate, okay. So once I find them equally, you can just, that means it's going to be half and half. So half and half. Okay. Same thing in the first question. In the first question, you had, I think, for 8 ohm and 8 ohm in parallel this way. Okay. Yes, you can use the formula 1 over R equivalent equal 1 over 8 plus 1 over 8. Yes, you can use the formula. However, in case if they are parallel this way, it's just one resistance half 4. If the two resistors are equal, that's a special case. If the two resistors are equal, so it's going to be half of the value of the value. Same thing if you apply this one. You got it? Any question? Okay. Okay, I think anyway. So I will give you the graded test. I will give you the solution. Please, you need to understand the mistakes because I am sure if you don't understand your problems, if you don't know how to make Stephen or Norton, we will do it again. We will do it again in the whole class. Same thing for current division and current division, voltage division. We will do it again. So you need to learn. Okay. Now I will move to the next chapter. Chapter 8. Okay, so I will give you overview or on what we will do in this chapter, okay? Before I give you the details. Look here, guys. First of all, there is something we need to agree on. We have when I tell you, you need to understand what is the difference when I say AC source or I say DC source. The source here can be voltage or current source. So AC here, it is actually alternating current. This one means direct current. Okay. So what is the difference between them? Either again, source here still can be voltage or current. Okay. Here in case of DC source, actually here it's if you have a time and voltage, so this one is going to give you constant voltage all the time. This is similar to the batteries we are using in our life. Okay, this gives you constant. If it is a current source, it's the same thing. It's going to give you constant current all the time. Is that okay? So once I tell you DC source, you should understand what it means. It means the value of the current is constant over the time. Okay. For AC source, no, it changes over the time. Okay, in AC source. However, we are interested on sinusoidal signals, sine waves. Okay, so here this can be the voltage, or it can be the current. Okay, guys, is that clear? Okay, in this chapter, I'm gonna focus on DC source. In next chapter, I'm gonna talk about AC source. So in this chapter, number 1, I'm gonna only talk about it's only for DC source. This is number 1. Number 2, next chapter, I'm gonna talk about AC sources. So for this chapter, we think about it. All the time we're gonna use DC sources. Okay? The other thing, what this chapter is about, as I told you before, if you have a resistance R and you have a capacitor this way, and then you have here a DC source, VS, which is DC source, okay? As I told you before, what should happen here if you have a circuit like this one? What should happen is, this is time and this is the current, I, I'm gonna call it IC, and then we have voltage here VC. So in the beginning, I can see there is a current IC, then the current will go 0 to 0. Okay. If you look at the voltage across the capacitor, this is VC. So you find the voltage increase, and then it's gonna be fixed equal to VS. This way. So you can see here, guys, if you connect a circuit like this one and the input is DC, because AC is a completely different story. I'm talking about DC input. In this case, you can, in the very beginning, you can see some current, okay? This current should charge the capacitor here. Once the capacitor is charged, the voltage across the capacitor is equal to Vn. Okay? Now I'm going to use two important terms. I'm going to use these terms all the time, okay? This period of time, we call it transient. This is the transient period or transient time. Transient. And this is a very short time. This is just in milliseconds, very short time. Okay? And this part here, from here until infinity, okay, this part is called steady state. Okay, steady state. So if I ask you, what is the voltage across the capacitor in steady state? So it should be Vs here. So there is some time in the beginning, we call it transit time. In the transit time here, the capacitor is gonna charge. Once it's charged, okay, that's it. So it's gonna continue in steady state this way. Okay. So this is just for a very short time, but this one is gonna continue. Okay. The one important thing here, very important thing in a steady state, actually the capacitor here, in case again the input is DC, I don't need to keep seeing it because if it is AC, it's a completely different story. The input is DC. So here in a steady state, the capacitor is gonna be acting like open circuit. So this circuit in a steady state should look like we have here R, and then we have here open circuit, and then we have here VS. And because the current is zero current, there is no current, the voltage drop here equal to VS. Right? There is no current. There's a voltage drop VS here, this one is still VS. There is no drop here, no current. Yeah? Any question here? This is big picture. So what I'm gonna do, this is half of the story. Because I'm gonna repeat everything again, but instead of using a capacitor here, I'm gonna use inductor. You will find almost everything is the same, but there are some differences. I will explain it now. Okay. In this chapter, I'm gonna explain in more details. So this is like a big picture. In this chapter, I'm gonna explain in details. We need to find equation. We need to solve the equation to get this response. But this is the conclusion. After you get the equation, after you solve the equation, that's what you will get here. Is that okay? For this circuit. Okay, now let's see if I put here an inductor. So if you have here R, here you have an inductor this way, and then you have here DC source, VS, okay? And then you have current R here. So what happens here, if you look at the relation, this time this is the voltage. If you go back, I want you to compare between these two. Here this is the current, here this is the voltage. We're gonna start from high voltage or some value, and then it's gonna go to zero. Now if you look at the current, here the current is gonna be current from zero, and then here is gonna reach to some point here. This point here, the current here is actually VS divided by R. This is the current. Okay, you can see the response here is very close to the response here. The only difference, current became voltage, voltage became current, as you see here. Same thing. This time here, we call it transient. This period here, we call it a steady state. You can see in case of steady state, in case of steady state, the inductor becomes like a short circuit. Why? Because you can see here, the voltage is equal to zero. So at a steady state, the voltage across the inductor is equal to zero. When the voltage across anything equal to zero, it's a short circuit. Okay? So here, that's why in a steady state, it becomes like voltage negative. We have here R, and then we have a short circuit here, it becomes this way. What is the current here? The current is actually V divided by R. And this is the same current I used here. So here, in this period, in this time, so I need some time until the inductor stores some energy. This is the period here. It stores some energy. Once it stores energy, okay, now the current it acts like a short circuit, and now because it's a short circuit here, the current is V divided by R, as you see. Any questions? Okay, guys. So this is what all this chapter is about. What this chapter is about, number one, I'm going to talk about this circuit. If you have R and C, I will give you for sure. This is not just a big picture. I will give you more details how you came up with this response. Okay. Same thing here for this one. How you came up with this source. Okay. Very important. I will study this specific case when you have a DC voltage. Listen to me because it's very important. I will study this specific case when the input is DC voltage, when you have a resistor and you have a capacitor. Okay? If your circuit is different, and we will work on different circuits. If your circuit is different, you have to make it like this one. To use the formula, we will calculate. So I'm gonna use this one, I'm gonna calculate a formula. Okay? And then all what you have to do is this formula only use when this is the circuit. Okay? If the circuit you have is not like this one, you have to make it like this one. What do you mean by you have to make it like this one? What do you mean? Okay, I will tell you. For example, here, if you have a circuit something like that here, yeah, this circuit is completely different than what I have, like the standard one. Okay, but if you take Thevenin again, Thevenin is difficult. Okay, if you take Thevenin here, so now it becomes you have R Thevenin, you have here B Thevenin, and now you have a capacitor. So now the circuit becomes similar to the standard, the one we'll study. We'll study this. You understand what I'm saying? So again, what I will do in this chapter number 1, I will study this specific circuit here. I will get some formula. This is the this is the result of the formula. Okay, you will see something similar to this one, but I wanna get a formula for that. Okay, so I'm gonna get some formula for this specific case, and then when I come to examples, when I try to solve the examples, sometimes if the circuit is like this one, you can use the formula right away. If it is not, you have to make it like this one. For example, here, if you make Thevenin here, it becomes like this one. Any questions? Same thing for this one. So here, that's the whole all this chapter is about. The whole chapter is about how can I get a formula for this one, how I can get a formula for this circuit, and then how I can use it in equation, in problems. That's it. Any questions? Okay. But now things are not. I'm trying to make everything easy. It's not difficult. It's easy, but you will have too many differential equation. It looks difficult, but it is not. Okay, because this equation, I'm trying to make it easy. So here I'm saying, okay, once you have a formula for this one, I can use it. But how can you get a formula? Formula here means the current and the voltage. So how you can get equation for the current and the voltage? Function in time, how can you get it? Okay, so actually to do that, because here I, the current equal to C dV by dt. Okay, so if you apply Kirchhoff voltage law here, you will find the equation you will make, it has derivative. What I'm saying? So if you apply, that's what we'll do. You apply Kirchhoff voltage law here, but I will have a differential equation of first degree. Same thing for this one. Also, I will have a differential equation of first degree. Why? Why you are going to have differential equation? Simply because the relation between I and V is actually differential here. Here, the relation between V and I is actually also derivative. You got what I'm saying? So again, let me summarize what I said. What I'm gonna do, guys, number 1, I'm gonna get equation here, okay? I'm gonna, from this one, I'm gonna get an equation. This equation is actually a first degree differential equation. First order differential equation. And then I have to solve this differential equation. Once I solve it, I will get a formula for I and VC. That's it. Once you get a formula for I and VC, that's it. I can use this formula in the example. Same thing here. Also, I need to find the formula here. Also, I need to solve differential equation. That's why what I'm going to do right now, I'm going to first order differential equation. I'm going to explain if you have a first order differential equation, how can you solve it? You get what I'm saying? It's not difficult, but I'm going to make very quick revision about it. Okay? But again, what I'm going to do right now, guys, I give you the big picture. What I'm going to do right now, I'm going to explain if you have a first order differential equation, how can you solve it? Is that okay? Why? Simply because if I want to find the relation between I and V here, in this one, this is the differential equation because we have derivative here. Same thing, I will have the same problem here. Okay? So that's why you need to learn if you have a differential first order differential equation, how can you solve it? Is that okay? So once I do that, once I show you how can you solve the differential equation, I will get a formula for this one, and then I get formula for this one. Then we will solve the examples, and that's it. This is the end of the chapter. Okay. So anyway, again, the equation should give you this response, but it should give you this response in equations, right? So for example, if I want to know after 1 millisecond what was the voltage current here, after 1 millisecond what was the voltage here, I need equation. So I want to get the equations here. Okay. So let's start with what I'm gonna do right now. I'm gonna explain how can you if you have first order differential equation, how can you solve it? Is that okay? Before I use it. Okay. Anyway, let's see. Okay. So this is the differential equation we wanna solve. Okay. You have here g x of t divided by dt, okay, plus a x of t equal to u, okay. So this is the equation. A is a parameter, okay. It's known. A and u are known, given to you, okay. I want to solve. So A and u are given. I want to solve this equation to get x of t. This is the unknown. This is unknown. I want to solve this equation. Everything else is known. So I don't know x of t. I don't know x of t. I know A. I know u. Okay. Here in this chapter, u is a constant value. It is not why, because I made it very clear. By the way, this u is coming from the source. When I told you when I make an equation here, I have to apply Kirchhoff's current law. When you apply Kirchhoff's current law, you will get an equation like this one. And because this source is constant, this C constant, so here in this chapter, u is constant all the time. Okay? This makes the solution easier, but u is constant all the time. It's not functioning the time. Okay, why? Because here we consider the case when the input here is DC. Okay, guys, that's okay. There is one more thing I want to explain here is about parameter A. Parameter A, there is here, I'm going to make a definition. We have something we call it tau. Tau actually is 1 over A, okay? And we call it time constant, okay? So I can rewrite this equation, and instead of writing here A, I can write 1 over tau, okay? So here we have something, just a definition, 1 over A, I'm gonna call it tau, and tau is time constant, I call it time constant, okay? And you will see later why this tau is important, because this tau, as I'm gonna explain later, because I told you this, the current has to come this way. Tau, this parameter, as I'm gonna explain, that's why I call it a special name. So someone can ask you, why you call this one a special name? Yes, because this one, as I'm gonna explain later, for now we call it time constant, okay? As I'm gonna explain later, this one, tau, can control how fast this can happen. So you can see how fast this one can go using tau. That's why I'm gonna just call it tau. Okay. So anyway, this is not gonna change the situation. You just have, so either here I can use A, but just because in the future I will call it here I can use it A, that's okay, or I can use it 1 over tau. That's okay. Still, here I want to focus on the mathematical part. You have equation. You have here derivative, first order derivative here, and then you have a number. This number is given to you, it's no number, it's constant, u is constant, and I want to find x of t. Okay. The solution here is x of t should equal two parts. One part we call it xn of t plus two parts xf of t. I'm sure in calculus you took differential equations. Is that right or? So anyway, so here you have here. So this one xn of t here. This one we call it natural response, or we call it transient response. Okay, so this is a transient response. This one here we call it forced response, or we call it steady state response. So it is like you have two parts, one part for the transient, one part for the steady state. Okay. So what's going to happen after we solve it? This transient should stay for short time, and then it's going to die. So this part for short time you have this part, and then after some time this part is zero, because that's exactly what happens. If you look at when I drew the figure this way, and when I drew this one this way, I told you this part is a transient. So during this transient, it's coming from this part here. Okay. After that, it dies. This part dies out. You will see how this part will, as the time increases, you will see as how the time increases, this part becomes zero. X of n of t is gonna go to zero. Okay. And now everything here will be related to steady state. Okay. So that's okay. So you are telling us now the solution. If you have an equation like this one, I'm very specific. If I have an equation like this one, this is the solution. This part I'm gonna call it transient. This part I'm gonna call it forced response or steady state. Okay. Let's start with this part here, the transient part. Okay. This one actually equal to A E negative A T. Okay. For sure, I can write it. A E negative 1 or T divided by tau, because I told you tau is 1 over A, so it's the same thing. Is that okay? What is A? A is unknown. I will tell you how can we get it. Okay. To get A, you need to know the initial condition. Okay. You need to know the initial voltage across the capacitor, because this will help you to know A. Forget A for now, but A is a constant value. I will tell you later. You will see how can I calculate it. But this is the response here. So can anyone think a little bit? Tell me why from this part here? Why this one is transient? Why this one is going to disappear over time? Can anyone think about it? Look at E, this E. When G increases, as T increases, E negative, AT is going to decrease. Okay? Until it becomes zero. Once it is zero, so this term is zero. So that's why I know this term is going to disappear. Because I'm saying you can see easily here, because of this part here, as T increases, this term decreases, the whole term decreases. That's why I told you the transient response is gonna die out quickly after some time. Is that okay? And who's gonna control if it's gonna die out for a short time or a little bit longer time? Tau. That's why we have tau here. Okay, so based on the value of tau, it can be something like that. It can be something like that. It can be something. So tau here, as I'm gonna explain for sure later in details. But now I'm gonna only focus on the mathematical part. But you will see tau is gonna control how long this transit will take. But the mathematical, the man is telling me this part is gonna disappear, because as you increase t, this part is gonna be close to zero. Okay. Any questions? Okay, so now to solve this equation, this is the first part here. Okay, what about the solution for this one? The solution for this one is very easy. It is just U divided by A. You have a proof in the slide, but we don't need it. Okay, it's just very simple proof. But the solution for this one is just U divided by A, and U is given to you. Okay, it's the same thing if I say tau times U. It's the same thing. Okay, guys. So now the whole response is x of t, the complete solution is x of t equal a e minus at plus u divided by a. This is the solution. Okay, this is the steady, this one is the steady state solution, this is the transit part. Any question? You guys, any question? Okay, so now the question is, have you solved it? No, I didn't still solve it because yes, A is given to me, U given to me, but still I don't need the uppercase A, I don't know it. That's why in order to calculate it, I have to give you x of 0, which is, for example, it should be given to you. I have to give you the initial value for x of 0. Okay. So for example, in case of a capacitor, here, this x is VC actually. So the voltage across the capacitor is actually x. So I need to give you V of 0 or VC of 0, which is the voltage across the capacitor. What is the initial value? What was the initial voltage across the capacitor? This is the initial value. Okay. So if I plug in here, so here x of 0 should equal to A times E minus A times 0 plus U divided by A. Is that okay? So using this one here, I can say A should equal to x of 0 minus U divided by A. Is that okay? So again, if you have an equation like this one, this is the solution, this way, okay? And in order to get this one, I have to give you the initial condition, this one, in order to calculate it this one. There is one more thing I want to say here is, by the way, this one here, U divided by A, sometimes we call it x of infinity. Because it's steady state. So what is the value? What is the value of x at infinity? Because if t is infinity, if t is infinity, this part becomes 0. So this part is equal to x of infinity. Okay? So that's why I can say also this equation becomes x of 0 minus x of infinity. Okay? Because the steady state is actually similar to x of infinity. If I put here infinity, this part becomes 0, with this one equal to x of infinity. Okay, guys, any questions? Okay, so let me summarize what I said. So what I said right now is x of t, the solution should equal to A E negative AT plus UA. Sorry, it was, U divided by A. That's what I said. Also, I told you actually A can be x of 0 minus x of infinity E of minus AT plus this one x of infinity. Okay? So yes, you can write the equation this way. This is one way, this is very important equation. We're going to use it all the time. I can rewrite the equation, this one, in a different way. I'm going to do simple manipulation here. I can say this one, x of 0, E of negative AT plus E of negative x of infinity times 1 minus E of negative AT. This is another form of this equation. So these are very important two equations. Okay. How they are a little bit different? Yes, they are a little bit different. Why? Listen to me. So again, let me give you the conclusion. The conclusion is you have a differential equation. I found that the differential equation. After I found it, I found two ways here, or two forms. This is one form. It can be this way, and another form it can be this way. How these two forms can have different meaning. Okay, they are equal, but they have little bit different meaning. I'm going to tell you before I finish, before we end the lecture. Look here. Actually, I can say for this lecture, this is the contribution, or this is the transient part. This is the transient part. Okay, so that's why this part is going to disappear after transit, this part is gonna disappear, okay? And this one is the steady state part. So this equation can show me this equation, just give me 1 minute, I'm done. But I wanna just wrap up this part. So this equation is gonna give me, from this equation I can see where is the transit part, where is the steady state part, okay? And this part is gonna die after some time. What about this equation, the other equation here? This equation here is gonna tell you, as I'm gonna explain later, because later you showed this equation, you have a capacitor. The capacitor has some initial value, V of 0, and then here you have Vs. So Vs actually is actually X of infinity. So you can see here, this equation can tell you this part is the impact. Sorry, I think I made it the other way. Yeah. No, I'm sorry. So actually, what I explained is correct, but not for this one. So here again, the solution I have two forms. This form here. This is for transit. I switch it, and this is for steady state. So one equation, this equation here, can give me one part for transit and one part for steady state. Okay, but if you look at this equation, this one here, this part is going to give me the contribution of the initial value of the capacitor. The initial value of the capacitor, how it's going to contribute, because this one is the initial value, okay? But this one is going to give me the impact of Vs. Again, let me summarize what I said to end the lecture. What I said, guys, here is, and that's what I'm going to continue next time. If you have a first order sequential differential equation, this is the solution. And this solution I can write in two different formats. They are the same, but it's going to give me different meaning. So if I write it this way, so here I can see the transit part, the steady state part. But if I write this way, here I can, this part actually, the impact of the initial state of the capacitor. How the initial value here is going to impact the solution. Here X of infinity actually Vs. X of infinity actually give Vs. Okay? So this, and this part is actually going to give me the impact of Vs. Okay, and I'm going to explain it. Any questions? Okay, good. Don't forget, we're gonna have a quiz on. I'm gonna distribute the test